All right, guys, so in this video, we're going to talk about optimization. And once you read a few of these problems that we're going to work, it'll be evident what we mean when we say optimization or optimize something. But generally speaking, we're looking to find the maximum or minimum value of some characteristic in a problem. And so we say that we're optimizing it. So we're going to take a look here on page 220 at number 4. So you can pause the video and go to your text and take a read of that problem. But what we're doing here is we're going to be finding the largest area of a rectangle. Now, largest area of the rectangle, that's a very broad statement, right? You can come up with any area of a rectangle, right? But there's always going to be a constraint to these optimization problems. We want the largest area of the rectangle, but it's got to be inscribed inside this parabola. And so the parabola that we're talking about is the y equals 12 minus x squared. And the picture that we're talking about then would be this guy right here. Here's our parabola, right? It's upside down parabola shifted up 12 units. And then we're going to figure out the largest possible area of this rectangle inscribed in it. So the biggest rectangle that could fit inside of there, okay? So for us, we're going to maximize the area of a rectangle. And so in general, we know the area of a rectangle is base times height. So in our picture, we should probably label things as such. Now, knowing how we're going to need to treat this, I'm going to call this point xy, which means that the distance from here to here would be x, and the distance from here to here would be y. That means for our area of a rectangle, we're going to need 2 x's to get that full base times our y. So the area of a rectangle is going to be 2x times y to start. Now again, that's great, but we need it to be subject to the constraint needing to fit inside the parabola. So you'll also notice many times when we set these up, you're going to have equations with 2 variables, but we don't want that. We want to get it down to one single variable. So in this case, it's going to kill 2 birds with 1 stone. We're going to not only plug our constraint into the problem, but we're also now going to get it down to one variable. So I'm going to take my y equals 12 minus x squared, and I'm going to plug that in right there. So my area now as a function of only x is 2x times 12 minus x squared. Now, this is the function that we are going to optimize. All of these functions will have, or should be able to be also bounded on a closed interval. Remember, we're only ever guaranteed absolute maxes and mins on closed intervals. So to construct this closed interval, what you should consider is the smallest thing that x could be and the biggest thing that x can be. Well, we know the smallest thing that x could be is, of course, 0, right? if it's not, well, we can't have a negative because it's a dimension, but it can go to 0 all the way up to whatever, whatever zeroes out this other part right here. And so when I just take this thing and I set it equal to 0 and I solve it, I get x equals plus or minus 2 root 3. But again, x can't be negative, so we're going to have to take the 2 root 3. So these are the endpoints now that I would circle back at the end to test for maxes and mins. Now, full disclosure, very rarely are these actually maxes and mins in the problem, because if you think about where we came up with them, they're not going to be very interesting values because they zeroed out the individual components. But we'll get to more of that here in a little bit. But for now, I've got my function and I've got my closed interval guaranteeing that I'm going to get what I'm looking for out of this problem. Okay, so we'll take this thing now to find the critical values. We're going to take the first derivative and we'll set it equal to 0. When all is said and done, this ends up being a 24 minus 6x squared. I'll set it equal to 0, and I find out that x equals 2 in this particular case. So that's going to be now another critical value that I take and I put on my number line, just like we did earlier in the chapter. I would test my endpoint, my critical value of 2, and my 2 root 3. When I do this, I get a 0, a 32, and a 0, Once again, these are generally pretty trivial. This is the number that I'm searching for because this would be my maximum of the three. And remember, I went into function A, went into this guy right here to find these values. Okay, so again, it's pretty evident right here that we've got a absolute maximum right here. And when it comes to answering the actual problem, what is the largest possible area? I'm going to also need to go back and find my y value. So if x is 2, and I take that into my constraint, 12 minus 4 gives us a y value of 8. And the area itself, remember area was 2 times x times y. So the area would be 32 in this case with dimensions of 4 by 8. Okay, dimensions 4 by 8, x by y, so 4 by 8. So again, the process here, guys, is going to be the same all the way through on each of these problems. We're going to have to put an equation together that we're going to either maximize or minimize. We're going to have to plug in the constraint. We're going to take the derivative, set it equal to 0, and then we're going to do the same thing we did in the first section of chapter 4. Now, I'm going to show you another way to kind of circumvent needing to work really hard on these here in the next example, but you can see we are able to construct these closed intervals like we would need to guarantee our result. All right, so the next we're going to look at then would be number 8 on that same page, 220. We're going to, looks like, we want to find the minimum length of fence required. So here we're minimizing, and if we look at what it is we're going to be minimizing, if we take this rectangle right here, and it's going to be divided, let's suppose I call this x, we'll call this x as well, then we would have 3 different y values, or not different, but 3 y values that we can mark. And for us, we want to minimize the perimeter of this thing. So the perimeter would be 2x plus 3y, right? The amount of fence needed. So all of this fence here, 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 and here. Now, again, it's going to be subject to a constraint. The constraint is the area. The area wants to be 216 meters squared. So that's going to be the constraint. But we know that area in our picture is x times y. So just like the last one, we have a function with 2 variables now. We want to get it down to 1, so we're going to substitute the constraint into that. Well, to do so, I'll probably go ahead and solve for a variable. So let's say y is equal to 216 over x. And now I've got my p of just x up here. So 2x plus 3 times 216 over x. Okay, so we've got our function. Now I'm going to come down and optimize it by taking that first derivative, setting it equal to 0, and solving. When I do so, my first derivative ends up being 2 minus 648 over x squared. I'll set that equal to 0, and when I solve it, I get x equals 18. All right. So x equals 18 off of that. To find my y value, remember now I'm just going back into the constraint. To find my y value, 216 over 18 gives us 12, which gives us now the dimensions of an 18 by 12 fenced in area. And then to find the actual perimeter, the perimeter would be where we just plug in the known values now. So we'd have our 2 times 18 plus 3 times 12, which gives us 72, looks like meters in this particular case. Okay, so let me talk through the setup here again. We wanted to optimize, in this case, minimize the amount of fence needed. So there's the equation for the amount of fence. But we wanted to make sure we had 216 meters squared of area. So the area in our picture was x times y. I solved it for y. I plugged it in. Then it's the same thing. Derivative set equal to 0, solve, and then answer the actual question they're looking for. Now, one of the things that I didn't mention in this problem, unlike the last one, was this whole idea of guaranteeing that we're going to get a minimum out of this. I haven't talked about a closed interval. But that being said, if I go now a little bit further, and if you remember, the second derivative will tell us concavity, of course, but it also helps us classify maxes and mins as well as kind of a secondary feature that's oftentimes overlooked. But let's take a look at this real quick. If I take my second derivative, which ends up being 1,296 over x cubed, remember, Rx is a dimension here, so it's always got to be positive. So if Rx is positive, then the second derivative is always positive. If that's the case, then what we're dealing with is concave up. And if we're concave up, then the value that we're studying, of course, is a minimum. So when all's said and done here, we are still convinced, now not even necessarily talking about a closed interval, we're still convinced that what we came up with now was the minimum value that we were searching for. So this second derivative a lot of times is a bit more efficient and a little more intuitive as well in understanding what you're dealing with in terms of a max or a min.